It's time for us to start finalizing our design for our linear power supply and building it into a permanent circuit. But before we do that, I have to address a problem that's come up as I've made these videos, and that is I'm not getting the current out of this power supply that I expected. I intended to build a 12 volt 4 amp power supply, but I'm seeing that with only a couple of hundred milliamps, my output voltage is starting to drop. So we need to troubleshoot this and find out what's going on. Let's start by looking at the basic design of the power supply and see where I might have gone wrong with my basic design ideas. This is the basic design of the power supply. We have an NPN pass transistor which provides 12 volts on the output. This is our load, which is essentially a variable resistance, and as that resistance varies it will demand different amounts of current, and this transistor has to keep the voltage across that load at a constant 12 volts. To do that, we're going to have approximately 12.7 volts on the base of the transistor. And to keep this voltage above 12 volts, I'm going to need greater than about 12.5 volts on the collector. This voltage can go higher, but if it drops down below approximately 12.5 volts, then my output voltage will drop. So let's look at the rest of the design and see what's going on at this point. Let's start at the beginning of the circuit, which is our step-down transformer. This takes the 117 volts AC off of the mains and steps it down to a more reasonable 12 volts AC off the output of the transformer. And when we talk about AC, remember, if there's no qualifier, we're talking about root mean square, or RMS voltage, which is simply a DC voltage that has the equivalent energy of our AC voltage. So what are we talking about when we have 12 volts AC RMS? We have a voltage that is constantly changing. It's going up and down and up and down, and it goes up to positive 16 volts and down to negative 16 volts and repeats that 60 times every second. So we actually have a peak of 16 volts, not 12 volts. Our RMS voltage is simply a DC voltage that carries the same energy as this constantly changing wave. The next stage in our circuit is a full wave rectifier, which takes the bottom half of this sine wave and flips it over. So now instead of going to positive 16 volts, negative 16 volts, back to positive 16 volts, we only have positive voltages. It goes from 0 volts to 16 volts, back to 0, back to 16 volts, and now it repeats that 120 times every second. The next stage in our circuit is a filter capacitor, and this acts like the storage tank of an air compressor system. So when our voltage goes up to 16 volts, it fills this capacitor up to 16 volts, but when the voltage tries to go back down to 0 volts, the capacitor cannot release or discharge its energy through these diodes because the current cannot go the opposite direction. So current comes through these diodes, fills the capacitor, but cannot get back the other way, so the capacitor charges to 16 volts and stays there. So our voltage goes up to 16 volts and stays at 16 volts. The next stage is our pass transistor, which is an NPN power transistor, which acts like a variable resistor that changes its resistance to whatever it takes to keep the voltage at the output a constant 12 volts, regardless of the amount of current that our load is taking. So our load just acts like a variable resistor, and as that resistance changes, it's going to demand different amounts of current. And the purpose of our pass transistor is to change its resistance to whatever it takes to keep the voltage across the load at a constant 12 volts. In order to make that happen, we have to put approximately 12.7 volts on the base of the transistor, and we expect to lose 0.7 of a volt between the base and the emitter, leaving us with positive 12 volts across here. So for this to work, we also have to have at least about 12.5 volts on the collector. Well, we've already determined that we have about 16 volts here. So that should be sufficient overhead to make this work. However, we have to back up over to the rectifier and realize that we're losing a little bit of voltage across the rectifier. In this part of the circuit where we still have alternating current, on the positive half of the cycle, the current travels through this diode and then to the rest of the circuit. And we expect to lose about 0.7 of a volt across this diode. So we start with 16 volts peak, and now we're down to about 15.3 volts. After going through the circuit, the current then goes through this diode, which takes about another 0.7 of a volt. So we lose 0.7 of a volt at the top, lose 0.7 of a volt at the bottom, so we lose about 1.5 volts. So starting at 16 volts across the transformer, we are down to about 14.5 volts by the time we get here. And on the negative half of the cycle, it works the same. We just go through this diode and this diode instead. So positive half, negative half, and we lose about 1.5 volts across the rectifier. So once again, we expect to have about 14.5 volts on the collector of the transistor, which is sufficient to make the circuit work. So where are we going wrong that my voltage is starting to drop when I draw only about 200 milliamps through this circuit? The possible culprits could be, starting with the transformer, maybe for some reason I'm not able to really get my 16 volts out of the transformer. Like any other component or even complete circuits, this transformer is going to act as if it were a single constant voltage source with an impedance in series with it. This is Thevenin's theorem. To simplify this, let's make this a battery with a resistor in series with it. For the purposes of what we're looking at, this will act the same as the AC generator and impedance I had there before. The impedance could be any combination of resistance, inductance, or capacitance, but for what we're going to look at now, a simple resistance will do. For now, let's just assume that it's acting like a 16-volt battery with a resistance of 1 ohm in series with it. So what we're going to do is put a load out here, which is essentially a variable resistance, and we will adjust this load to get different amounts of current coming through this circuit. I'm not going to worry about what the load is. I'm going to be concerned about what the current is. So let's just put a current meter here to monitor the current and see what happens to the voltage across the load. First, let's make this an infinite load. So let's take the resistance out of here. And so now we have no circuit at all. There's no current flow. And to have any loss in voltage across this resistor, what do we need? We need resistance and current. So whenever we have current flowing through a resistance, we're going to have a backup of voltage where the current enters the resistance, and then a lower voltage where the current exits the resistance. Since this voltage doesn't change, because this is a constant voltage source, the only thing that can happen, if this voltage must be higher than that voltage, then we will have 16 volts here and something less than 16 volts here. But once again, we don't have any current flowing through here, so we cannot have that voltage difference. So we start with 16 volts, and we have 16 volts across this open circuit here. Now let's put the load back and adjust that load until we have 1 amp of current and see what happens to the 16 volts. So we have 1 amp traveling this direction, and we're going to have a higher voltage here and a lower voltage here because you always have the higher voltage where conventional current enters the resistance and the lower voltage where the conventional current exits the resistance. This voltage must be 16 volts, so this voltage must be something lower. And so we have 1 amp going through 1 ohm. According to Ohm's law, we will have 1 volt across this resistance. Once again, higher here, lower here, so we start with 16, we lose 1 volt, and we have 15 volts across the load now. So with a 1 amp load, we lose 1 volt coming out of the transformer. Remember, this battery and this resistor represent the whole transformer. So simply taking an amp out of the transformer, assuming that the transformer has an internal resistance of 1 ohm, we're going to lose 1 volt for 1 amp. Now if we double this current, of course, we're going to double the voltage lost across this resistor, and this will drop down to 14 volts. And if we continue that up to 4 amps, we will lose 4 volts, so we'll only have about 12 volts across the load at 4 amps. So it's conceivable if the output impedance of this transformer, represented by this resistor, is high enough that if I put a 4 amp load on here, my output voltage might not be high enough to operate the circuit. Now we needed at least 12.5 volts on the collector of the transistor, and we expected to lose about 1.5 volts across the rectifier, so we need about 14 volts peak off the transformer when that transformer is delivering 4 amps of current. So let's test that transformer and see if we can get at least 4 amps out of it when our peak voltage drops down to 14 volts. So what I have here is my transformer. I have a rheostat so I can put some load on it and draw some current out of it to see what it can do. So what I need to do is simply put a voltmeter across the transformer, put the load across it, and put a current meter in series with it so that we can measure the current and the voltage and see what the voltage is when we get 4 amps out of it. Unfortunately, I don't have a AC current meter to do this. So how am I going to do this? Well, there are certain things I could do. I have a 1/10 of an ohm resistor here. I could put that in series and measure the voltage across it, and that would make an impromptu current meter. And so I would get 1 volt for every 100 milliamps that was traveling through the transformer. But my AC voltmeter really doesn't have the resolution. I would be at a 200 volt range, and I'd only be looking at the last digit to look at 100 milliamps, 1 volt per 100 milliamps, and I don't think I'm going to be able to trust the accuracy of that using that method. So I could use an even bigger resistor, but then I would be affecting the whole circuit by adding more resistance. So I don't want to use that method. So what can I do? Well, it's pretty simple. I can just go ahead and set it up without a current meter, and I will adjust this rheostat, not even caring what resistance it is, adjust it until my voltage drops down below a peak of 14 volts, and then I will measure the resistance. So then I know, knowing the resistance and the voltage, a peak of 14 volts and whatever resistance I have here, I can divide that resistance into my voltage, and that will tell me how much current I was getting. So let's go ahead and do this. I'm going to go ahead and get a couple of clip leads and put that at its maximum of 100 ohms. Put a couple of clip leads, make sure I'm not clipping the same lead onto both ends of that. I guess I should have picked a different color, but we'll be good to go in a second. And so now we have a load on there of 100 ohms. Let's put the oscilloscope on there. I don't have my ground lead on my probe here. I don't feel like going to look for it. So I'm just going to hook the oscilloscope ground here. That'll work just fine. Hook that up there. Actually, it would be better if I do that over here, closer to the transformer. So let's ground that. Hook that there. And there is our output. I can hook up my trigger over here to stabilize that a little bit. There we go. Okay, let's see what we need to do here to make this measurement. We have the probe set at times 10, so my voltage is set at 0.5 volts, which means it's 5 volts. Since this is 0.5 volts, this is a times 10 probe. I multiply that by 10, so that's 5 volts per division. So I have 5, 10, 15. There's my 16 volts. Let's do a little adjusting here. Set my coupling to ground. And set that right at the middle. Set it back to DC coupling. So there's my sine wave as I described it. It's going up to 16 volts, down to minus 16 volts, back up to 16 volts, just as we expect. To get a little more accurate reading, what I'm going to do is ground this again, and I'm going to move my 0 volts down to the bottom. Remember, wherever this line is, when I set that to ground, that means this is showing me where 0 volts is, and so I can move my 0 anywhere I want on the screen. And anything above the line is positive, anything below the line is negative, so I'm just going to move it down to the very bottom of the screen so that I'm only seeing positive. Flip that up there, and I'm going to set this up at 0.2 volts per division times 10, so that's 2 volts per division. Let's double check our ground here. There we are. And so 0 volts is at the bottom, so it's 2, 4, 6, 8, 10, 12, 14, 16 volts is kind of going a little bit off the scale to give us our 16 volts. So now what I need to do is start loading this down and watching that peak voltage. So I know when the peak of my sine wave goes below 14 volts, that's when my output of my power supply is going to start dropping. So the question is, can I get 4 amps out of this transformer before that peak drops below 14 volts. So here goes nothing. Let's increase the load. Before we do it, let's just take a look and see what we're looking at. So it's 2, 4, 6, 8, 10, 12, 14. So the second line from the very top is what I want to watch. When the peak of this sine wave drops below that line, that's when I'm getting my maximum current I can get from this transformer. And let's see if that maximum current is 4 amps. Crank up the load, more load, more load, more load, more load, more load, and the voltage is dropping, and whoops, a little bit right there, disconnected. All right, so didn't want to leave that too long. Well, that's warm, that's warm. Okay, now I just need to measure this resistance. Put this meter on the 200 ohm range. that right there. Now let's see how much resistance we have in this rheostat. 2.3, 2.2 ohms. It's stabilizing at 2 ohms. So 14 divided by 2, that's 7 amps. I kind of find that hard to believe. Let's double check that. Let's take the ohm meter off. Let's check it with another ohm meter just to be sure. Well, I just checked it with 3 different ohm meters and they all gave me different readings, probably because it's such a low resistance. But they averaged out to about 3 ohms. So let's say 3 ohms, that's going to give us a little over 4 amps. So the transformer is not our main culprit. So let's see what else might have conspired against us to drop that voltage too low. So the next part of the circuit to look at is our bridge rectifier. We expect to lose about 1.5 volts across that. Let's test it and see if that is correct. Okay, now since I'm measuring DC voltages, I'm coming off the rectifier and I put the filter in there. Since I'm measuring DC voltages, I can go ahead and use my meters and not have to use the oscilloscope. And the question is, how much current can I get out of the whole system before the voltage at the capacitor drops below 12.5 volts? So I have the transformer coming into the rectifier, that's going to the filter as you've seen before. Coming off the filter, I'm coming to my load, from my load through my current meter up here, down to ground, and then I have my voltmeter across the capacitor. And as we can see with about 100 ohm load, I have 140 milliamps and about 14 volts. Now what I'm going to do is increase my load until that drops down to 12.5 volts and see how much current that is. Now I've been cheating all along here. These are 1 amp diodes here, so this is not ready for my full 3 amps. But I don't think I'm going to get 1 amp out of it anyway, but I want to be careful and not let the smoke out of my diodes. But anyway, here goes. I'm going to increase the load and watch the voltage, and when it gets down to 12.5 volts, let's see how much current we are taking. So here's more load, more load. We see our voltage is going down to 13.5. 13, 12.5, and that was 500 milliamps. So there's our culprit. It's these diodes. I was only able to get 500 milliamps before this voltage dropped down below 12.5 volts. So I'm going to get 500 milliamps at best. So what went wrong with my thinking here? Well, what went wrong is I was just being quick and dirty about it. I was thinking I knew I would have to have some voltage overhead, and I was thinking, 4 volts ought to be enough. I want 12 volts out. I'll get 16 volts peak out of my transformer. That should be enough. Obviously, it's not. And the transformer's up to the task, but these diodes are not working as expected. So what's going on here? Well, what we can do is put one of these diodes in series with the load and measure the voltage across it instead of the voltage output. We'll crank up the load until the current gets up to 500 milliamps and then see how much voltage we have across here. Should be 0.7 volts, right? Well, let's find out what we really get. So here's my voltmeter. That's this lead. Put that at the, I want to put that at the anode. Put the black lead at the cathode. Now we have to make this part of the circuit. I'm going to need another clip lead to do that. So coming off of this, okay, now we are going through the diode. Watch my colors, kind of got my colors backwards here. Okay, so we're going through the diode, current is going that direction from the anode to the cathode. That is correct. Okay, and look at that. Right now I only have 130 milliamps flowing through that diode, and I already have 0.8 volts instead of 0.7. Let's crank this up to a few hundred, to maybe 500 milliamps and see what that does. 200, 400, there we go. Oops, don't want to take it too high. About 500 milliamps, and we've got 0.9 volts across it. So we're getting a whole volt at only 500 milliamps. Those are 1 amp diodes. Let's see what happens if we crank it up. Let's see if we can get a whole amp through those. 0.9, half an amp, 6/10, 7/10. We're getting over a volt across that diode. What the heck is going on there? If you've learned nothing else in this course, you should have learned that when we talk about a silicon diode having 7/10 of a volt across it when it's forward biased, that is only a typical voltage. If we have enough current going through that diode, we can get considerably more than 7/10 of a volt. These particular diodes can have as much as 1.5 volts across them at 1 amp. So what's happening is at 500 milliamps, we're getting almost an entire volt across each of these diodes. We were expecting only 7/10 of a volt. What's that done to us? So instead of only having 1.5 volts across the rectifier, we're losing about 2 volts across the rectifier. And at 4 amps, our peak voltage off our transformer has dropped down to 14 volts. So we're starting with 14 volts, we're losing 2 volts across the rectifier, leaving us with only 12 volts for the collector of the transistor, and we need at least 12.5 volts for the circuit to work, best case scenario. So what's happening is that only 500 milliamps, our voltage at our collector of our transistor is dropping. The circuit here that's controlling the base voltage can no longer compensate for the drop in voltage across the output, and so the output voltage starts to drop. So what can we do to fix that? One popular solution is to replace the standard silicon rectifier diodes in the rectifier with Schottky rectifier diodes. A Schottky diode has a typical forward bias voltage, even at higher currents, of only about 0.5 volt. So that would be a quick solution to get our voltage back up to make this circuit work. Another solution would be to replace this transformer with one that has a higher output voltage. The next higher common output voltage is 24 volts. So let's see how that affects the rest of the circuit. Before we put that transformer in, let's see how much power is being dissipated by this transistor with the 12 volt transformer. So let's take a look at a best case scenario of plus 16 volts at the collector of the transistor and 12 volts at the emitter. So now we have 4 volts across the transistor. And let's assume that the load is demanding 1 amp of current. So with a 12 volt transformer, we have 16 volts, 12 volts, giving us 4 volts across the transistor, and 1 amp. To find the power that's being dissipated, we multiply the current times the voltage, so 1 times 4 gives us 4 watts. That may not sound like much, but without any electromagnetic radiation or mechanical motion involved with this transistor, that's going to be 4 watts of pure heat to get rid of, and that's a lot of heat, believe it or not. In fact, you could easily blister your finger on that transistor if it doesn't have a really good heat sink on it. Now let's see what happens if we increase the transformer to 24 volts. Now we're going to get approximately 30 volts on the collector of this transistor. So we start with a peak of about 34 volts. We're going to lose a couple of volts across the rectifier, so that's going to leave us with like 31 volts. Well, we'll put it 30 volts just to keep the numbers even. Let's have that same 1 amp of current going through the load. So 30 volts and 12 volts, that means we have 18 volts from the collector to the emitter of the transistor. So we have 18 volts, 1 amp. To find the power being dissipated, we multiply them together. Now we have 18 watts of heat to get rid of on this transistor. So with a 12 volt transformer, I had about 4 watts to get rid of. With the 24 volt transformer, I have 18 watts to get rid of, more than a 4-fold increase. So we have to make a compromise between our transformer output voltage and our final output voltage to keep the voltage across our pass transistor reasonable so we don't have too much power to dissipate. So this is a good argument in favor of switching power supplies which dissipate much less power in the pass transistor. But remember, this project is not necessarily to build the best power supply we can, but it's to learn how we can string a few simple components together and make a useful circuit out of them. We'll talk about switching power supplies at another time. One advantage of using the higher voltage transformer, though, is I could make a variable output power supply that gives me anywhere from maybe 0 volts to 2 volts, depending on the regulator design, up to as high as 24 volts, depending on how much current I can get from this transformer and keep its output voltage high enough to give me that 24 volts. So now it's decision time. Do I want to replace these rectifier diodes with Schottky diodes and stick with my 12 volt output? Or do I want to go with a higher voltage transformer and have the versatility of a higher output voltage? I just have to deal with the extra heat being dissipated by this transistor if I do. I'll make that decision before I start the next video when we actually start building out this power supply. But that's it for now. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.